Just a moment. Okay. Well, thank you, Alexander, for arranging things across multiple continents. It's quite impressive that you've managed to pull together all sorts of people. What I'm going to say today is about not invariants generally, with some specific examples, and some thoughts about the various uses of not invariants. Of course, if I start about knots, we all are familiar with various knots. And what we think about is a simple closed curve in 3 space, where equivalence, or I'll talk about 2 knots as being essentially the same, if you can manipulate one to the other as a piece of elastic rope. So this knot will sort of undo itself and turn into the trivial knot. A knot invariant is generally something number, polynomial, something maybe algebraic that's associated to a knot. And the point is that the invariant ik has got to be the same as ik prime when the knots k and k prime are equivalent. My own interest in knots is primarily from a geometric viewpoint. So I'm especially interested in invariants that will help with geometric questions of one sort and another. Of course, the most basic one is to tell knots apart. If you've got 2 knots, can you decide if they're equivalent? Well, the geometry, you may be able to manipulate one to the other, but if you can't, then an invariant is the sort of thing that comes to your rescue. You could ask things about how simply the knot could be drawn, how many crossings and things like that. You could ask what sort of 3-dimensional spaces you might be able to construct starting from the knot. All sorts of nice ways of making 3 manifolds out of knots. You could identify some geometric features of the knot and related structures. What sort of surfaces can it bound? Is there any particular underlying structure to the way that the knot lies in 3 space? You know, it might be a fibered knot, it might have some other nice geometric properties. And I'm inclined to think of an invariant as interesting if it answers some of these questions. Now, of course, you could turn these questions on their head and use them to describe an invariant. You could talk about the crossing number of k, the smallest number of crossings in any diagram, braid index of k, smallest number of strings, all sorts of indices. We had Sergei looked the other day at the Thompson index for constructing them from a Thompson group, any sort of thing like that. But of course, that sort of invariant isn't generally terribly easy to calculate, because in principle, you've got to look through all possible diagrams of the knot to answer it. And that's not really a feasible thing to do. On the other hand, I'm inclined to think of a not invariant as good if it's one that can be readily calculated and compared with invariants of other knots. sort of thing I'm thinking about is being able to calculate it from a diagram. And of course, from this point of view, our goal is firstly to make the interesting invariants good, be able to calculate them. And secondly, if you've got a good invariant, what is it? Make it interesting. What is geometrically important about it? So those are the sort of underlying principles, you might say. Now I'm going to go back a few years for one invariant that is both good and interesting, the classical Alexander polynomial that was produced by Alexander almost 100 years ago now, which is an integer Laurent polynomial, depending on the knot. Familiar sort of things, trefoil, figure 8, on knot. And as an invariant, it's good in the sense that it can be calculated from, you give me a diagram and I can calculate it for you. And shall I say, it's become even better over the years with different strategies for calculating it. Fox, for instance, free differential calculus, Seifert using spanning surfaces, Conway, partly with skein theory in mind, and Kaufman as well, combining some of those, show up more geometric features. So this all adds to its interest. Now, I'd like to make a slight variant of the sort of way I'm going to look at knots, just because it fits better with some of the calculations. I'm going to deal with oriented banded links. So the only difference is thinking of them as made of a flat piece of tape rather than a bit of rope. So you get pieces like this. And equivalence then is moving the flat tape to itself. So the only difference really between this and the rope is that you can get extra twists. You might refer to them as framed links rather than banded links. And it's quite convenient to draw them implicitly by standard diagrams if you use the blackboard framing convention where the tape really follows the plane of the diagram. And of course, if you do have a twist, you can draw a little kink in the diagram to make it go along with this convention. The reason I'm doing these is one of the useful things in the hunt for invariants of a knot is that you can use satellites of the knot. Satellites, particularly Schubert wrote large amounts of very interesting stuff in German, and he wasn't very good at putting down theorem, etc. You had to read the material to see what he had actually proved. But there are some very beautiful things in his large paper in Acta Mathematica. And satellites, of course, are things where they're sort of offspring of the original knot K. You start with a banded knot K and you decorate it. You make it a little bit more complicated by choosing a pattern Q and placing the pattern around the knot, something like this. A pattern is a diagram in the standard annulus. You take the annulus containing Q and place it around the band neighborhood of K, and then the result is the satellite that I will call K star Q of the original knot K. So there's K with my framing convention. So it's a trefoil with an extra little twist there. let's think of Q. One of the simplest patterns is the 2-cable pattern that I've drawn in the annulus, and you just run the pattern around the knot K. That's what I would call K star Q. Now, I mean, geometrically, of course, a satellite, if you're thinking of 3-manifold terms, the exterior of a satellite has got the exterior of K in and among it in a very intrinsic way. So really, it's quite natural to think of satellites in the same terms as K when you're thinking about K. In particular, when K and K prime are equivalent as banded knots, then decorating them both with Q, you get equivalent knots. So, of course, what you then know is that if I is a banded knot invariant, then you could use I on K star Q to think of this as another invariant for K, for a fixed choice of pattern Q. And it might be that you might be able to choose Q so that even if K and K prime are not distinguished by I, K star Q and K prime star Q might be distinguished by I, and so you would have another way of telling them apart. In classical terms, if you've got the classical Alexander polynomial, there isn't any gain in looking at satellites. It was one of the nice things of Fox's work, Torres and Fox, that there's a very simple formula for the Alexander polynomial of a satellite of K in terms of the Alexander polynomial of K itself and something to do with just the pattern itself. I haven't exactly spelled out how that works, but it's it really just does depend on K and Q. R is the winding number of Q around the annulus. And the upshot of that is that if K and K prime have the same Alexander polynomial, then so do K star Q and K prime star Q. So you won't get any gain invariant-wise by looking at this. Now, I'm going to jump forward a few years in the sense that the Alexander polynomial was an invariant that surprisingly turned up in a totally new construction by Jones in 1984. He constructed a new invariant of oriented links, and it was very quickly extended to this 2-variable invariant P, which was named either the Humphrey polynomial, the initial letters of 6 of the 8 people. I hate acronyms, and I used to call it P or the 2-variable polynomial, but that wasn't very helpful. And then actually all 8 of the people are sometimes put in as Hump-flipped. The important point about this polynomial is it specializes definitely to the Alexander polynomial, putting that variable v equal to 1 and z in a suitable way, and the original Jones invariant. So if I might make a historical diversion at this point, 1984, end of 1984, these turned up, and 1985, after this P had been discovered, it was in principle, it was a relatively good invariant. You had ways of calculating it. But there wasn't, the interest was needing to be looked at. You know, how did it work geometrically? I mean, that's still an ongoing story a bit, but it's getting much more resolved. But I tried to find out a little bit more about its behavior on satellites because of the geometric relations. And I had very much the Alexander polynomial in mind, so I was expecting to be able to calculate P of a satellite in terms of P of the knot and something to do with Q. I wasn't sure what, but I was thinking that this would be the way it would work. So I had a couple of different knots, K and K prime, that I knew had the same value of P. And I was working with Hamish Short at the time, who knew a little bit about computing. So we set about computing P of K star Q, P of K prime star Q to look for clues. Now, the knots K and K prime were, they could be presented as closed three braids. Actually, K is essentially the 2-7 torus knot, but I put that other bit in to get the banding, to get the twisting to agree properly on the two. K prime looked a little bit more complicated. You join the top and bottom. And of course, if you're going to make the satellites of these using the pattern Q, you have to replace, you know, each crossing in the original knot will get replaced by 4. And there'll be one further crossing coming from this little crossing in Q. So altogether, the diagram for K star Q is going to have 33 crossings, and the other one was going to have 49 crossings. Now, bear in mind that at this stage, computing power wasn't terribly large. We were working initially as a pilot on a BBC Model B computer, which had 64K RAM. So we were having to be careful. And we started off with the resolving tree algorithm to try and calculate. And it actually hit home to us very quickly, this phenomenon of exponential growth, because we got so far, we got about to 23 crossings and it was working. And you could see that the next crossing was going to take however long. It was going to take us about 3 weeks to get to 28 crossings. And we said, oh, well, we're going to need to use the mainframe. Now, the mainframe was about 1,000 times more powerful. And then somebody pointed out, well, that'll get you another 3 crossings. So they then said, you need a better algorithm. Well, based on a different feature of P, we managed to produce a much better algorithm. It had quadratic growth under the conditions that we were working with, and it worked well, but it really underpinned my appreciation of the difference between polynomial growth and exponential growth. When we'd done our calculations, we were surprised to find that the answers we got were different. If this is right, the invariant P K star Q is independent from P of K. Of course, we were a little bit cautious in that if you're doing computing and you're wanting to show that two polynomials are different, but if you make a mistake in the computing, they're almost bound to be different when they show up. So we said, well, we hope we're right. Then we calculated other examples, and we got an extra rather nice little surprise. These two knots, which we were able to compute with Q with a little bit more care, showed up the same polynomial. So question was why? And of course, one of the possibilities was that, again, these two knots are particularly closely related geometrically. Turning over the piece in the square on the left-hand one gives you the right-hand one. One of these knots, of course, was due to Conway, and he knew about these sort of knots, and he called them mutant pairs. And Alexander polynomial is the same on mutant pairs, and people actually knew that the Humphrey polynomial was the same on mutant pairs. So a suspicion was that maybe this is a feature of mutant pairs. We tried out some more examples, and it did seem to work. And then other people were able to prove that it always held. So one of the mottos in dealing with knot invariants is to look out for geometric features. For more complicated patterns, Q, by the way, this doesn't always hold for mutants. When Q is a three-stranded pattern rather than a two-stranded pattern, you will get a difference. And just one other little historical point there. I worked on this the following year with Paweł Traczek, one of the Humflipped people. And he was used to working with very limited resources in Poland. So he suggested, well, we wanted to show that these were different for a three parallel. Why don't we can just about squeeze something, but we couldn't calculate the whole polynomial. So specialize a variable, put z equal to 2, maybe v equal to 3, and work with your coefficients modulo 19. And if you get a difference, well, bingo. And if you don't, try it again, modulo 23. Well, it did work. Now, a slight difference again is that fairly rapidly after that, other invariants of knots coming from very different sources showed up. Here's one general whole family of these things are invariants, one parameter invariants that can be constructed for any time you have an irreducible module W over a quantum group. Right, well, people had examples of irreducible modules in quantum groups. And in particular, the quantum groups of the special linear series, SLN, there is, rather like SLN itself, there is an irreducible module W lambda for each partition lambda of number, a positive integer M. And one thing that happens with these ones, again with mutants in mind, is if you've got a module W and W tensor W, which is a module, it decomposes into irreducibles. If the irreducibles don't have multiplicities, that is, they break up into pieces which are all inequivalent, then mutants will have the same invariant when you construct the invariant with W. So that's, that explains, in the end, some of the observations before. But of course, when you come across an unfamiliar invariant, maybe unfamiliar to you and familiar to somebody else, it's very natural. In fact, it's an important thing to do is to look for relations with familiar ones. And those quantum group invariants turned out to be very much related with the Humphrey satellite invariants. They could be identified as specializations of them. If you played your cards right, you could get one lot from the other. One nice thing is that there is a pattern that sort of mimics what happens when you get the quantum invariant with W lambda, depending again on the same partition lambda. And a rather nice feature of it is that if lambda is a partition of M, the partition specialists write it that way, the pattern Q lambda can be realized with a pattern with M strands around the annulus, or maybe a linear combination of these. So when you've got these, you can translate results between the different viewpoints. And the nice thing about that is that some things that are obvious from one viewpoint may not be obvious from the other. Now, I did note earlier that if the W tensor W decomposed into irreducibles without multiplicity, then the invariant would not tell mutants apart. W tensor W, though, breaks up, first of all, in a two-stage process. It decomposes as a symmetric and an exterior part. And it's interesting that you may have a module where the symmetric part has no multiplicities, the exterior part has no multiplicities, but maybe there is a multiplicity, at worst then 2 of a module on W tensor W. So you might look at modules that decompose this way. And just for the purposes of this talk, I'm going to call such a module special, because there turned out to be a nice result about special modules. They include, by the way, all partitions of M up to M less than or equal to 5. The other stronger condition only went up to M equal to 2. Lambda being a hook, I should have maybe drawn you a hook. Those of you that know about partitions know that a hook is a partition with an arm and a leg and nothing else. But if you then look at all the modules for partitions, the smallest one that is non-special is a 27-dimensional SL3Q module for the partition, a partition of 6, that is 4 and 2, which is not a hook. Now, I want to look at a little recipe for mutants. I want to think of a knot, of 2 knots, made up from two tangles, A, B, and C. And there's K. I want to focus on A, and B. These are, there might be anything inside that box A, but there have just got to be 2 strings coming out the top, 2 going in the bottom. Ditto for B and C. And there's K prime. You just swap over what's in the boxes A and B. The Conway and Kinoshita Terasaka pair can be drawn in this way. There is the box A, B, and C. and you swap them over. So they do show up in that way. But something that turned up rather later on was that Jun Murakami, well, I think maybe it was Ochiai and Morifuji initially, were looking at some rather special sorts of tangle, and they came up with a pair of tangles with the surprising property that the polynomials were the same even with 3 parallel strands. So again, the question was, what was special about them? What was special about the pieces A, B, and C that he and Ochiai had used? And eventually I identified the important feature in their tangles, that both what was put in the box A and what was put in the box B were symmetric under the half twist. Now, if I go back here, this box, it's symmetric under the half twist, but this box isn't. So that was the feature that they had come up with. And what I was able to show was that if you colored your 2 knots, K and K prime, by a special module W, if A and B both have this half twist symmetry, then the mutants will have the same, the 2 knots will have the same invariant. Now, because all irreducible modules are special for lambda partition of anything less than 5, it then follows that satellite invariants with less than or equal to 5 strings, which can be calculated from these modules, will have the same Humfly polynomial for any pattern with less than or equal to 5 strings. So as long as K and K prime are built out of 2 tangles with the symmetry property, then K and K prime will have the same invariant. Pretzel knots turn out to be a very fruitful source of examples of this sort. On the top is the pretzel knot K1, 3, that's 3 twists, looking right-handed, left-handed, left-handed. And in the second box, the second one, I've swapped over these 2 boxes. To make it look like the picture of the A and B, you ought to imagine this turned through 90 degrees. And of course, these 2, what's in this box is invariant under, well, what I would have required was invariant under rotation about the horizontal axis. So if these are invariant under rotation about the horizontal axis, which would be true for any pretzel knot, then you can swap the order of boxes at will. Of course, if I had just had those 2 boxes and left out the other ones, well, I wouldn't have got a different knot at the end. So K and K prime, we think K and K prime are different knots. At the moment, let's say we'd need to be sure, but they will have the same invariant for satellites with 5 or less strings. So just to be absolutely sure, I made the calculation for K and K prime in the first non-special module that I could lay hands on to see if they still had the same invariant. And the results showed that they were different. So actually, they really are different. Just a word on this one, by the way. I didn't calculate the Homfly polynomial, but it does tell us that there is a 6-string pattern for which they differ, the invariants. And there is no way that I could possibly calculate the Homfly polynomial of k and k prime with this 6-string pattern on, even with more modern techniques, because that would involve an awful lot of crossings. On the other hand, I did have to get, you might say, down and dirty on the calculational line, in that I had to work out the quantum invariant for that 27-dimensional module, which relied on certain 27 squared by 27 squared matrices and identifying little pieces among them by bits of linear algebra. One more piece, though, on this whole problem. There are some n-string patterns, Qn, for which k and k prime decorated by Qn have the same invariant, P, for arbitrarily large n. And these, among them, are the actual cable patterns. If you thought about the N1 cable or the NM cable, because the translation from the Homfly invariants to the quantum invariants, it turns out that for cable patterns, all you have to look at are hook partitions, and all the hook partitions are special. It follows that these must be the same for arbitrarily large n. So I was rather pleased with that result on symmetry for mutants that have special symmetry, give you a flavor of invariants that have got more similarities and more geometrical togetherness. So just as a sort of sum up, beware if somebody offers you a new invariant. Well, beware, keep your eyes open when somebody offers you a new invariant of knots, because it's quite possible that it's some combination or specialization of familiar ones. So you need to look at it with interest and with caution. So look out for clues where the invariants that you've got differ, what features that they can or can't distinguish. You know, one thing that I'd also looked out for with Paul Melvin in the past was why is it possible that the SL2 invariants, the colored Jones polynomials, and the Alexander polynomial had something in common? And it turned out they did, because neither of those lots distinguished mutants. I should also say at this point, yes, subsequently there have been all sorts of very interesting invariants. One of my favorite lot are the Vasiliev invariants, finite type invariants, because they have, again, shown they turned up in a very unfamiliar context in terms of singularity theory, but Berman and Lin managed to point out that they also, lots of them showed up in terms of the Humphrey polynomial, its satellites, other sorts of polynomial and things, and they give a beautiful cross section because they have a feature that finite type invariant of degree k, there are only a finite number of independent ones. So if you've got another one, it's going to be related to things that you already know. Skein theory, which I did and didn't hint on, is one of the things that shows up in a lot of the stuff that I've definitely been interested in. And lots of that goes back to John Conway. I call him the father of Skein theory, along with all sorts of other algebraic goodies. He had a particularly good knack of finding memorable terms for lots of his innovative ideas. Tangles, I've talked about, mutants, I've talked about, these are Conway's terms, and skein. Skein, of course, goes back to knitting and knitting wool. My grandmother used to have skeins of wool that she wrapped up into balls. So there is a skein, but figuratively, it's also bits of things that get rather tangled up. And if I can let Conway roughly have the last word on this, he used to say that you should do two things when you think you have a new invariant. Firstly, you need to show that it distinguishes two knots that can't otherwise be told apart, and make sure it's independent of your other things. And then you have to produce two knots that it can't distinguish, so that you can carry on having the fun. So I think I will stop at that point with just a note of a source for some of my material. Thank you.
So thank you very much, Hugh. Are there any questions?
Yes, may I ask a question? Hugh, I have two questions actually. One of them is that a satellite invariant can detect orientation or not? Can you get something which would distinguish orientation?
I don't know of one that does. Not the sort that I've been. I think that, yes, I certainly any of the quantum, even the sort of extended ones, and the, I mean, you can use patterns that go round both ways as well, and things like that. You can use other invariants. I don't know of one that does.
Okay, I see. All right. And my second question is, you know, in this, it is about for Color-Jones polynomial, you have that tail and head. So some parts of the Color-Jones polynomial are stable when you take like a higher and higher dimension representation there. And for those examples which you have when this home fly are different for satellites not, is there any sort of head and tails which are stay the same and they're different somewhere in between? So is there any kind of stabilization like this head and tail for Color-Jones polynomial, but for home fly?
I think, I mean, if you, well, let me see, I mean, colored, now, if it's Color-Jones, you're talking about, I mean, if you talk about one particular color. You've got SL2 fixed.
Yes, yes, yes.
And then you're changing the color, but you move along the colors. If you're talking about the Humphrey satellite ones, you've got an awful lot of extra things to go. I mean,
Right.
for mutants, none of your hooks will tell you.
I see.
Things for for some of those symmetric ones, certainly.
Mm-hmm. Okay.
So any of the symmetric or anti-symmetric pieces, but no, I think that's about as far as I could say.
Right. Okay. Okay. Thank you. Thank you.
Okay, are there any other questions? Okay, then let's talk. Let's thank you again for this nice talk, and with this, essentially, we wrap up the event. Thank you for participating. Just if you have a little interest, as I said in the beginning, there will be maybe a little bit of more talks sometime in July by a couple of people whom I wanted to invite, but I couldn't, and so you're welcome to tune in if you like. And then that's it from me. Thank you very much for joining, and maybe I hope that I can see some of you also physically sometime in the future when this terrible pandemic is over. And okay, so
there was a question in chat.
Yes, right. Yes, right. I forgot. So you maybe you can say something about this.
I'm not sure how that works. I've never really properly identified. You could, in principle, I think, if virtual knots can be realized as knots on a higher genus surface, you can have satellites of knots. I mean, you can have a skein of things on a higher genus surface. I mean, I'm familiar with the torus. It gets more complicated if you do other things, but yes, in principle, I think you could in that way. I would need to be careful about how, if you've got satellites, if you have got them on a higher genus, if you realize the virtual knot on a higher genus surface, to be sure that it goes along with the equivalence when you change the genus. So can I then finish up again by, on behalf of us all, thanking Alexander for organizing this whole series.
It was my pleasure. It was my pleasure. Okay, so
thank you very much.
It was a first attempt, you know. Maybe we'll have an opportunity for something better later, but okay, so we can start small. Yeah, okay. Anyway, thanks everybody for tuning in and for your interest, and maybe I will see some of you someday later. Okay. Thank you.
Thanks then.
Bye.
Bye.
Bye.